So this video clip is about information cascade, which is a particular type of groupthink. So setup is like this. We got restaurant A and B, and each patient will see a signal SA and SB. SA says A is the best restaurant, and SB says B is the best restaurant. So the prior information the patient has is that A and B are equally good. So they have half probability that they are the best restaurant. And the true positive rate, which is that we see signal A when A is the best restaurant, and we see signal B when B is the best restaurant, is 3 quarters. The false positive rate, which is we actually see as B, but actually A is the best restaurant, is actually a quarter. So that is our information set. The decision rule is something like this. The patron calculate the posterior belief based on the signal. So here actually we need to have a lower have a subscript which says either SA or SB. So if the posterior belief is actually larger than half, then we'll go to restaurant A. If it's smaller than half, we'll go to restaurant B. If it's exactly the half, so the patron is indifferent between A and B, we will go to whatever the signal says we should go. So now let's look at the actual development of the event. We'll go have a restaurant A and B. Let's say the first patron comes in and he sees signal A. So we want to calculate PA conditional on SA. Okay, and it can be easily written out. So if we write out the whole base rate and plug in the value, we will find that the posterior belief that A is actually indeed the best restaurant, given that we signal A is 3 quarters. So according to our decision rule, actually the first patient will actually go to restaurant A. Now let's talk about the second patient. Okay, suppose that the second patient actually receives a signal B. What would he do? So we need to calculate. First we need to figure out what is his information set. His information set is that he sees a patron in restaurant A, so he knows that the first guy got SA for sure. Now I got SB. So what is that tells you about the posterior rate. So here actually we stuck because we actually do not directly know what this two value is. But let's have another assumption that says they are conditional independent, so that PSA SB conditional A is equal to PSA conditional A times PSB conditional A. So let me add here. The assumption is that signal is independent. And so is conditional B, which is the same thing, which is PSA conditional B. So now then if I plug in the value here, I got, so if the second patron actually got a signal which is contradicts the first signal, the posterior belief about A is the best restaurant is exactly the half. So it will exactly be equal to the prior. So it does not actually give you any other information. And according to our decision rule, the second patron will actually go to restaurant B. So let's say when you are third person and you walk into the restaurant, you see that the first two patrons goes to 2 different restaurants, and you know that they must have SA and SB. So according to our calculation so far, there's no new information at all. Okay, so you are exactly the same as if you just walk in and saw nobody before you. Okay, now let's consider a different situation where the second person actually receives a signal SA. Okay, so now we need to calculate PA conditional SA. Here we have the same problem that we need to get the posterior value for these 2 quantities. And by the same calculation we get before, it is easy to get that they are, if you actually see that the second person also get a signal SA, you have very strong reason to actually go to restaurant A. So that's the decision rule for second person. So now let's consider the decision rule for third person. Let's say he get a signal SA, okay, and you can calculate what is this value turns out to be. By the similar calculation, you will get it is, I guess, 27 over 28. So you have every reason to go to restaurant A. So that's the case. Now let's calculate this another quantity, which is if you get signal SB. Okay, so by the similar calculation, what actually we need to calculate is P SA SB conditional on A, and what's the likelihood that you get SA SB conditional on B. So this is work out to be 9 over 27, and this, oh no, 9 over 64, and this is going to be 3 over 64. So the posterior will be 9 over 9 prime 3, which is 3 over 4. So even if you get a signal B, the posterior belief still tells you that you should go to restaurant A, because if the first person has already been in restaurant A. Okay, so that means whatever signal the third person get, he will go to restaurant B. So now let's consider the signal for the fourth person. Okay, let me mark it properly. So the first person will come in and he will get either signal A or signal B. So we need to ask what is his information set. If he sees 3 persons in restaurant A, he knows for sure that the first 2 persons actually got signal SA, because otherwise they will be in different restaurants. But he has no idea what the third person got, because third person, no matter what he got, he will actually go to restaurant A. So he will basically ignore the third person. There is a mathematical reason for that, but we are not going to the details. It's just intuitively it didn't matter. So all he need to know is that first person, second person get a signal A. So his calculation will be exactly as third person. So basically he will calculate this 2 value, and he will decide that it is better for him to go to restaurant A. So that means that's the same for the first 5, 6, 7, 2, as many as you want. Okay, and from the third person to the last person, all they know is that the first 2 persons actually go to the restaurant A, and their signal will be irrelevant. Okay, the tricky part here is to notice that although if you get 2 SA in a row, it is very likely that A is indeed the best restaurant. There is still a non-negative chance, which is actually works out to be here is 1 in 16 that A is actually wrong. So the groupthink here, the herding, is mostly right, but they still have a small chance that actually it turns out to be wrong. And that is what we call information cascade.